In the previous video, we studied how to use logistic regression to compare events between groups. And today, we will learn Poisson regression, which compare rates of events. So to compute rates, analysis involves time. And next chapter, we will learn survival analysis, which is another analysis of time to events. Although today we are learning rates concept, I'd like to make contrast between analysis comparing rates with Poisson regression versus Cox regression, which analyze time to first event. Today's motivating example is from a paper published in New England Journal of Medicine, assessing effect of tiotropium versus salmeterol for prevention of exacerbation of COPD. This is a randomized, double-blind, double-dummy trial with a follow-up of 1 year and 2-arm parallel group trial. And they used two analytical approach. First, using Cox regression using hazard ratio. So this is the result they stated. Tiotropium as compared with salmeterol increased the time to the first exacerbation with a 17% reduction in the risk. Fantasy hazard ratio 0.83 and 95% confidence interval 0.77 to 0.90. P-value less than 0.001. In another analysis, they used Poisson regression and they indicated tiotropium reduced the annual number of moderate or severe exacerbations. 0.64 is the rates, annual rates, 0.64 versus 0.72. And rate ratio is 0.89. Okay? And p-value is 0.002. Rate ratio is 0.89, indicating 11% of risk reductions of moderate or severe exacerbations with the treatment. P-value equals 0.002. And this is a table, and they compared two groups on serious adverse events. So they use rate per patient year, okay? And then they use Poisson regression to compute rate ratios. So let's talk about difference between rate ratio. You'd use Poisson regression in hazard ratio, and you'd use Cox regression. This is a hypothetical example. Patient number 1 is followed for 120 days. Okay? And after 20 days from randomization, and this person first experienced the event. And after 40 days from randomization, and another event occurred. And after 80 days, and another event occurred. So there are 3 events occur within first patient. And the second patient was followed for 60 days. And the first event occurred at 30 days from randomization. And the second event occurred at 45 days from randomization. And the third patient was followed for 40 days, and there was no event occurring with this person. And rates of events is compared counting total number of events within a cohort. In this case, total of 5 events, okay, divided by total follow-up time. So 120 days for first patient, and 60 days for second patient, and 40 days for the third patient. So you add this up and get 220 days. Okay? And I converted 220 days to a year, which is 0.6 year. So in order to compute annualized rate of events, you divide total number of events by follow-up year, total follow-up year, which is 8.33 events per 1 year. So we call this annualized rate of events. Interpretation of this is 8.33 events occur if one person is followed for 1 year. For rate, we put the unit per person year. Okay? So if you go back and look at this table, we can interpret this as events of infection occur 2.69 events of infection occurs for 100 patients if everybody followed for a year. And that means 0.0269 events occur if one person is followed for a year. That means risk of infection within a year is 2.69%. Okay, so similarly, and you can interpret this as risk of events of infection is 3.15%. And take a ratio between these two, and that converts to rate ratio of 0.85. This indicates risk of infection is reduced by 15% if you use tiotropium versus salmeterol. So what happens if you explain this by hazard ratio, where Cox regression is typical choice to compute hazard ratio? So Cox regression we use when we analyze time to the first event. Therefore, in this analysis, we only use data up to until the first event. So, ID number 1, first event occur at 20 days from randomization. Second patient, first event occur at 30 days from randomization. And the third patient, no event occur during entire follow-up time. So if you compute rate for the first event and you only count 2, and then total follow-up time would be 20 plus 30 plus 40. So that is 90 days. And 2 over 90, it is 8.11. So actual computation of a hazard is not really the same as rate, although based on the fact Cox regression used time to first event, hazard would be similar to the rate, including only the first events. And another computation we can do is marry proportion of events. So proportion of events, and we ignore time element. So what we do is we divide number of patients who experience event over total number of patients. So in this case, it provides 0.66. So if you follow patient over a year, and 67% would experience events. If you take a ratio of 2 proportions, that provide relative risk. Later this video, I'll show you how to compute relative risk using Poisson regression. So let's use SPSS to compute rate ratio. Today's classroom example use Framingham Heart Study. Dataset names framingham.sav. So let's open SPSS. So the dataset of framingham.sav contain data from 4,700 patients. Framingham study is a prospective cohort study. And in this example, outcome of interest is events of coronary heart disease. First exercise, we want to analyze effect of age on coronary heart disease. So since we compute rate, and we need 2 groups to compare. So let's create 2 groups based on age. In Poisson regression, we actually don't need to dichotomize exposure variable, and you can analyze continuous exposure variable. And I'm dichotomizing this only for a classroom example. Okay, so we use compute variable, and age 50 would be 1 if age is grade 50 or greater. Otherwise, this would be 0. Okay, so now we have binary variable by age. So to compute the rate, we first need to compute total follow-up time. So we are going to add this follow-up year within the patient whose age is 50 or greater, and separately within the patient whose age is less than 50. And we also need a number of events, coronary heart disease. So we will add up number of events within each group. Alright, so to compute summation within a group, there is a very useful function in SPSS. You go to data and aggregate. We want to compute summation of CHD fate and follow-up year. So you put the both variable under summaries of variable box. And we want to compute by each age group. So we put age 50 under break variable box. Okay. So default function is set to mean. And what we want is total number instead of mean. So we are going to change this mean to sum. Okay, so let's highlight both and click on function. And you change default of mean to sum. Okay, and click continue. So now the function is changed to sum. Okay, and we are going to create new data set which contain only the aggregated variables. So let's click this middle option and give name to this data, new data set. So I call it sum and click OK. Right? SPSS create new data set, okay, which is this one, right? So now you have total number of CHD fate and total number of follow-up time within the group whose age is less than 50 or whose age is 50 or greater. So what is next? So to compute the rate of coronary heart disease, and you simply divide total number of events by total number of follow-up time. Okay, so default format for SPSS is set to showing only 2 digits after decimal. So let's change this to higher number of digits. So how can we interpret this? Unit is follow-up time is a year, right? So you can say if we follow one person over a year, 0.01109 person would experience CHD. So that means risk of one person develop CHD is 1.1% within a year. Similarly, the risk of developing CHD for one person for a year is 2.195% for patient whose age is 50 or greater. So to compute ratio, you simply take ratio between these two numbers. So 0.0219 divided by 0.01109. Okay, so that is a rate ratio. Okay, so to compute rate ratio, and you simply divide rate of CHD within the patient whose age is 50 or greater divided by rate of CHD for a patient whose age is less than 50. Okay, so that is 2.0. Some people may analyze this data by ignoring follow-up time and simply summarize data by 2x2 table. Okay, let's do that. So you go to cross tab and you include CHF fate and age 50. Okay, and then click OK. And this 2x2 table is showing, and probably better to add percent. So let's add percent of CHD within each age group. So that is a column percent. So you go back to cross tabulation table and click on cells and add a column percent. Okay. So the 2x2 table show there is 27.3% chance of having CHD for a patient whose age is less than 50. There is 38.6% chance of having CHD for a person whose age is 50 or greater. And then when you take a ratio of these two proportions, and that provide relative risk. So relative risk ignoring follow-up time is 1.4. In rate, considering follow-up time is 2.0. Rate ratio is much larger than relative risk. Let's think why. Why rate ratio is higher than the relative risk? Difference between the two is one considered time, other ignored time. This graph showed distribution of follow-up time. In Framingham study, patients were followed maximum to 32 years. So in the younger patient, there are actually a quite large number of people who are followed for more than 30 years. On the other hand, patients who are older, they started being old. Not many people could probably survive such a long time, and therefore they end up having much shorter follow-up time compared to younger patient. So, if analysis ignore this differential follow-up time, and what do you think could happen? Okay, so rate ratio, consider this differential follow-up time. So, you divide number of events by total follow-up time, and therefore the rate you are considering is rate per person year, for example, for older patient and also for younger patient. So by dividing by total follow-up time, and you standardized the unit for this rate being constant for both group, such as 1 year per patient. Okay, so therefore the rate ratio controlled for the differential follow-up time. Okay. Although the relative risk computation does not involve time component, therefore they couldn't consider effect of differential follow-up time. So what happened is, when computing relative risk, you consider follow-up time is relatively the same, therefore you ignore the differential follow-up time. And because follow-up time in younger population is larger than follow-up time in older population, so given that, what happened is, if you account for differential follow-up and older people having shorter follow-up, that actually make actual rate larger, and rate of CHD among younger population is smaller. So numerator get larger and denominator get it's smaller. Therefore, the rate ratio is larger than the relative risk. So in this case, which relative risk or rate ratio do you consider being valid, or more accurately reflecting actual risk in each group? Of course, rate ratio, right? So even when the number of events are same in older and younger, let's say 100 events occur in older and 100 events occur in younger, and you may think there is no association, but if you only follow up older population in 1 year and you follow up younger population for 5 years, and of course same number of events reflect totally different frequency of events. So in that case, rate in older population become 5 times larger. And that makes sense, right? This number of events, same number, 100 events occur in 1 year versus 100 events occur in 5 years. So therefore, it is very important to consider the differential follow-up in computation of risk. And many times such ignorance of differential follow-up time bias the result of the study. Another example, when you conduct randomized clinical trial comparing effect of a new drug versus placebo drug, and you followed patient over a year, and you counted number of events, which is deaths, for example, at the end of the study, and you had the same number of deaths between two groups. Although you realized patients who received placebo are dropping out much earlier than the patient who had the drug, because they knew they are not getting new drug, therefore they were less motivated to continue study. So in that case, if the placebo group followed shorter amount of time than the new drug group, and number of events eventually ended up being the same. If you consider that differential follow-up time, you may conclude drug actually worked, because placebo group, same amount of patient died within the shorter time. And if the people who dropped out early on stayed to the end of the study, they could observe the events. So that will increase number of events in placebo group. So it is very important to use a method which can correctly account for differential follow-up time to accurately assess effect of exposure of interest. In previous video, we learned how to use logistic regression. Logistic regression is for binary outcome variable, events versus non-event. Therefore, differential follow-up time cannot be considered in the analysis. Same for relative risk. Relative risk computation ignore time component. Therefore, you can't control for differential follow-up time. Rate ratio, as we saw, it can accurately control for differential follow-up time by computing rate using total follow-up time. And choice for the regression for rate ratio is a Poisson regression. So next video, I'm going to show how to perform Poisson regression to compute rate ratio using SPSS. Next chapter, and we will talk about survival analysis. Survival analysis is another technique to handle differential follow-up time. Okay, so we will be learning Cox regression to compute hazard ratio. And surprisingly, there is no common choice of regression for relative risk. Now, although we can use Poisson regression, ignoring the time to compute relative risk. So we are going to, in the next video, learning how to perform Poisson regression for rate ratio. I also show you how to use Poisson regression to compute relative risk. And GEE, generalized estimating equation, is a special technique to handle assumption of Poisson regression. So we will be talking about this in detail in the next video.